Hello, welcome to this AQA Further Math Statistics video, the second in the Continuous Random Variables 1 series, looking at probability density functions. In the first video, we looked at the fact that the normal distribution curve is an example of a probability density function, or PDF, and that would normally be written with the notation little f of x, function of x. And we also looked at the fact that with such continuous distributions, we will be working with probabilities of the type that I'm illustrating here, where perhaps we're looking at the probability that x lies between 11 and 11.5, and the probability is equivalent to the area under the curve. So here you have a neater version of that, and a reminder that the probability is obtained by finding the area under the curve, and that may either be a probability you find by integration, or it might be just some simple polygon that represents that area, so you can evaluate it without integration. Obviously, with the normal distribution, the integration's not possible, so you're going to be using your calculator or tables for that. Probability density functions have to fulfill two specific conditions. The first one comes from the fact we know probabilities cannot be negative, and therefore that means our probability density function must always be greater than or equal to 0. And that means that it must always lie above the x or the horizontal axis. And we also know, because the sum of all probabilities possible has to equal 1, we know that the total area under that curve must always equal 1. And these two conditions must be met by any function that is going to be a probability density function for a continuous random variable. So here are those conditions just identified separately for you, and we can use these as a checklist to see whether a particular function can be used as a probability density function. So firstly, the curve's always above the x or the horizontal axis, and secondly, the total area under the curve must always equal 1. So to look at an example here, and you might like to just pause for a moment and read this example through, we're looking at our probability density function f of t. We've got the variable t because we're looking at time. And it's a very simple function, just going to be a straight line function. Do notice that this probability density function is defined as only being relevant for a specific range of values for t, and is equal to 0 otherwise. And this is very common with probability density functions. They are modelling a situation, but only for a part of the possible range of values that could be involved, and here just 0 to 10. And what we have to do is sketch ft, and you might like to use a graphics calculator, although this is very simple, to sketch it. But remember that if you're asked to do this in an exam, or you want to really see what's going on, we are only interested, and it's only relevant to look at the function between the values that are given to us, so between 0 and 10. And then we're going to just check those two important conditions to make sure that this indeed is a valid probability density function that can be used to model this situation. So the sketch is very, very simple, because we just have a straight line. And if we have a look at the first condition, is that function always above the t-axis, or is it always greater than or equal to 0? That definitely is true, because we can see that quite clearly. If we then check the other condition, is the total area under the curve equal to 1? Well, this is a very simple curve. So the area under the curve, actually, we're just talking about the area of a triangle. We could integrate if we wanted, but it's pretty simple just to look at half multiplied by the base, that's obviously 10 units across, and the height, which is 0.2, which is the value of f of t when t equals 10, and that clearly equals 1. That's correct. And you could, if you wanted, evaluate that integral as an alternative way of checking that. So that would also work out for you the total area under that curve. So both the conditions are met. F of t is a probability density function that's valid to model the particular situation in terms of length of phone call. Now again, you might like to pause a second, just read through this second example where we are modelling the length of time it takes to complete a half marathon, and our probability density function f of x is again only defined for a specific range of outcomes for x. So obviously all runners in this club are expected to complete the half marathon between 1 and 4 hours. And if we look at the function here, it's clearly a cubic function. You can use your graphics calculator to sketch it. If we look at the whole function, just remember the general shape of a cubic function. If we look at the value of f of x when x is 0, it's going to be -2 and a bit. If we look at where we cross the x-axis, clearly we're going to cross where x is 1 and x is 4. And if you think about the cubic shape, we're going to get this sort of function coming out here. It's not very well drawn, but you get the general idea. We've got a point where x is 4 where we're going to touch at the x-axis, but we actually cross the x-axis where x is 1. And we are only going to be interested in that portion of the curve between x equals 1 and x equals 4. And here's a much neater version of that, just simply looking at the part of the graph that we are interested in. So this is our probability density function. We need to do the checklist. So certainly that function is above or on the horizontal axis, so is greater than or equal to 0. So that condition definitely is fulfilled. And then if we have a look at the second condition, does the total area under this curve f of x equal 1? Well, this is a much more complicated one to work out, so the way we would have to do that is to actually integrate our function, and quite a complicated thing to integrate. You have to multiply all that out first. You could check it on your calculator if you want to do it that way, but we need to make sure that this area under the curve, so the integral of f of x between the values of x equals 1 and x equals 4, we need to check that that equals 1. And in fact it does, so that second condition is satisfied. So f of x is a valid probability density function to model how long it takes to run a half marathon. And that's the end of this second video in this series.